All right, hi, Math 219 folks. This is Dr. Sweeney, and I wanted to go and talk a little bit more about chapter 4.3. The stuff is actually really difficult, and so I at least want you to get some of the basic ideas here, and then kind of help you work through some of the problem solving. So let's take a look at this problem. This problem is inside of the OneNote. It's an activity that I did in my in-person class. And so it says, suppose that you're an inspector in an auto parts factory. The acceptable levels of defects in a batch of 1,000 is 1%, and you selected a random batch of 1,000 parts. Okay, so assume that the parts, the part defects are independent. So what I want to do first is I want to determine, right, if this is binomial. So there are three requirements for binomial distributions. The first is that we have a yes or no. So in this case, right, defective or not defective is my yes or no. And so yes, that actually works. That's yes or no. Either is one or the other. Second, we want to independence of trials. Now, if you notice, it says that part defects are independent, so we have independence of trials because it says so. Because the scenario says so. All right. Then third, we need a fixed number of trials, which oftentimes means that we need a finite sample size. And in this case, we get that. That's n equals 1,000. Okay. So this is a binomial distribution because all three of the requirements are met. So all three of the requirements are met, so consequently that makes this a binomial distribution. Okay. Oh, that's actually the next question. So there it is. All right. Next, now what we need to do is we need to figure out what is the probability. We're looking for an actual probability. Now, one of the key ideas is to understand that what we get when we work with a probability distribution is we are looking for the probability that we get a certain number of successes. So in that case, that is a certain number of defective parts out of 1,000. Okay, so a certain number of defective parts out of 1,000. So if I look, what is the probability that between 2 and 4 parts are defective? Well, one, I need to identify that n, my n size is 1,000. Right? It's 1,000, yes. Okay. And my p is going to equal 0.01. Okay. And, excuse me. Place. So n is equal to 1,000. And p is equal to 0.01. Both of those things are really crucial in order for us to be able to find probability. Then the next part is I actually want to write out in symbolic terms what it is exactly that I'm looking for. In this case, I'm looking for the probability that I'm going to have between 2 and 4 defective parts. And I'm actually going to change this to 100. We'll just, it says 1,000, I'm going to make it 100 for the sake of. And this one 100. So now, what I'm asking now is what's the probability that if I select 100 of them at random, okay, so I select 100 parts at random, that between 2 and 4 of the parts are going to be defective, all right? So I'm going to use StatCrunch in order to find this. And so I've made a recommendation that you use StatCrunch in order to do this. It makes life a lot easier. So I go to Open StatCrunch. I'm going to go Stat, it's under Calculators, and it's the binomial. Okay, so the binomial calculator, in this case, I'm selecting 100, n equals 100, and the probability that I get a defective part is 0.01. Okay, and then because I'm looking for a range of data, instead of using what we call the standard, I'm going to use between, and it's going to be between 2 and 4, and so I'm going to put those in here into my probability statement. Okay. All right, and so that gives me my answer, 0.2608. Okay, so that's it. It's equal to 0.2608. And if I write what that means is there is a probability of 0.2608 that between 2 and 4 parts per 100 will be defective. And so, kind of to help you conceptualize this, this is essentially the probability that we get 2 defective parts plus the probability we get 3 defective parts plus the probability that we get 4 defective parts. Okay, so that's actually how we think about this. So what did I do? Well, I figured out what my n is. That's the set number of trials. Then I figured out what my probability was from the scenario. Okay, and we look up here, the batch of 1,000. Okay, batch of 100, excuse me, and the probability of defects of 1%, which is 0.01. All right, now what about the probability that x equals 0? Well, in this case, n hasn't changed, so n is still 100. P is equal to 0.01. And this is the idea that in a batch of 100, 0, exactly 0, will in fact be defective. So what I'm going to do is I'm going to go in here, I'm going to go back to StatCrunch, and this time I'll use my standard calculator. Okay, and I'll set it equal to 0. All right, and compute. And in this case, we see that it's going to be 0.366. Probability that x equals 0 is equal to 0.366. Okay, so there is a 0.366 chance, the probability or likelihood, that 0 of the 100 parts are defective. And so that's how we use our calculator. What you'll notice here are a couple of things on the calculator. One, you have to be able to discern what n is and what p is. Two, what you'll notice if I click that, you're going to get all these different signs. So you're going to have to be able to figure out what those signs are. And that's one of the reasons why I use this probability notation. The other is that it kind of helps me to think about my problem. And then if I actually want a range of them, I can utilize this between part of the calculator. And so that should actually be pretty handy for you too. Okay? All right. Now, and so like for D, the probability that at most 5, okay, the probability at most actually means x is less than or equal to 5 parts. Okay? And then I would go in, utilize my calculator, standard, at most 5 is, so that's less than or equal to 5. And that's 0.9994. So it's almost certain. That equals 0.9994. Okay, that's it, right? I generally, what I would write down, I'd write down my n equals 100, my p is 0.01, and then I'd find my probability using the calculator. Now, this next question actually has to do with understanding how the binomial distribution works and how it's put together. So it's a probability distribution, which means that it has a mean and it actually has a standard deviation because it's also quantitative. So all the values that the binomial takes are either going to be are quantitative variables and they're numbers of successes, so they're counts. All right. So if I look at this, and let's say a batch of 100. Okay, again 100. So n is equal to 100, and p is equal to 0.01. Now we actually have formulas for determining the mean and standard deviation of the distribution. So mu, our mean, is going to equal n times p, which is 100 times 0.01, which equals 1. So what we expect out of the 100 is we're going to expect 1 to be actually broken or defective. We expect 1 to be defective. And this mu equals n times p, that's the equation for the mean. Then I need a standard deviation. Sigma is going to equal the square root of n times p times 1 minus p, or we also sometimes use square root of n times P times Q, where Q equals 1 minus P. So basically, probability of success times the probability of failure. So that's going to be, in this case, equals 100 times 0.01 times 1 minus 0.01, or 0.99. So it equals 100 times 0.01 times 0.99. Okay? So 100 times 0.99 times 0.01. And then we square root it. Is going to be 0.9949 or 0.995. So this is approximately 0.995, and that's the standard deviation. Now, if you remember from 2.7, we actually have a rule for determining if we have an outlier or an unusual score, and that rule is that if it's more than 2 standard deviations away from the mean. So what we want to do here is we're going to find the z-score for 4 or more defective parts. So z equals 4 minus 1, because that's the mean. So that's x minus mu over sigma, right, divided by 0.995. Okay? So that's going to be 3 divided by 0.995. And that's 3.0151. Okay? So that's 3, it's approximately 3.0, or excuse me, let's look at it again. 3.015. Okay, 3.0515. All right. Now, all we need to do now is interpret that. So to interpret that, what we get is since the z-score for 4 is 3.015, this means that 4 is unusually large for a number of defects. Because it's greater than 2 standard deviations away from the mean. And there it is. So what we want to do is we want to use the fact that I can find a mean and standard deviation, the mean being n times p, right? Okay, and the standard deviation, sigma, is going to equal the square root of n times p times 1 minus p. Once I find that mean and standard deviation, then I'm just going to use what I know using the standard deviation rule to determine whether or not I have an outlier or not. And so consequently, I found the z-score. The z-score was greater than 2. So what does that mean? That means that 4 is in fact an outlier. All right. So with the binomial distribution, what you want to do is you first want to make a determination, am I using the binomial? And you utilize the definition in order to figure out if that's the case. Once we do, it's pretty much just a matter of figuring out what your sample size is, n, what your probability of success is, p, okay? And then utilizing what's inside of the question to figure out what probability am I looking for. Then I go find the probability, and then I interpret. Okay? And that's essentially what you're trying to do. Use StackCrunch for this. It makes life so much easier. I can't emphasize that enough. All right, I'll talk to you soon. Bye.